Hey everyone, today I'm going to be presenting our new paper for ICASSP 2025. This is a collaboration between Imperial College and Meta, and it's entitled Contextual Speech Extraction, Leveraging Textual History as an Implicit Cue for Target Speech Extraction. Me and Minzu are joint first authors on this paper, and the remaining authors are Hong Li, Stavros, and Maya. So first of all, I wanted to motivate the task that we're going to be presenting in this paper. So I'm sure most viewers have probably heard of applications such as speech enhancement, speech extraction, and also speech separation, and also audiovisual speech extraction and enhancement. So in practice, what these tasks are aiming to do is to take a noisy speech sample, so a sample where multiple speakers are speaking at the same time, and to extract only the target speaker's speech, which we entitled to be our clean speech. The thing is, in order to do this, we need to tell the speech extractor which target speaker it should be extracting. There are multiple ways to do this. The most traditional one in target speech extraction papers is to use an audio embedding. So what you do is you tell the speaker to go into another room, record a 5-second sample of themselves speaking in a quiet environment, and then you use that as your cue to understand what the target speaker sounds like. In practice, you do this via feeding into a neural network and getting a speaker embedding, and then the speech extractor knows, okay, this is what this person sounds like. I'll extract only that person's speech. Another way to do it is to turn on the webcam and record the video of the speaker, and then by the lip movements, you can tell that the lip movements are synchronized with one of the speech streams and not with the others, and you extract only that one. You can also have like a text prompt where you tell it like extract only the loudest speech or the speech in French. And also you could have like a spatial cues if you have multiple microphones and you know the position of the speaker in the room. Now the problem here is that all of these are pretty cumbersome. So asking the speaker to stop using the app and step into another room to record a clean sample of themselves is pretty annoying for the speaker, and also it's problematic to store this. Asking the user to turn on the webcam is not necessarily good in most use cases and not very practical. And also, if somebody else steps into the camera, then there's no way to know which of the two speakers in the camera we should be extracting. And spatial cues, obviously, with multiple microphones, require have other requirements. And yeah, text prompts also require some explicit input. So we're wondering, can we do speech extraction without any of these like really annoying to obtain cues? So the scenario that kind of came to mind was mobile messaging. So in mobile messaging, I'm sure you've noticed that a lot of people use voice messages, and a lot of the time they're recorded in noisy environments. So it's a good application for speech extraction. Another thing that's remarkable in this application is that the voice messages are interleaved with text messages. So let's look at an example here. Two speakers are speaking, and the first one says, "How are you doing?" Responds, "Not bad. What about you?" "I'm a little tired." "How come?" And then we have a voice message with multiple people speaking at the same time. Let's say I'm in the supermarket and I'm recording it there. One person is saying, "I'm going to buy some oranges." The other person is saying, "Have you watched the latest episode of Game of Thrones?" And then finally, I'm saying, "Work has been very busy recently." As a human, we understand not only because I know what the other speaker sounds like, but also because I understand the context of the conversation, that "work has been very busy recently" is an appropriate response and the others are not. So the idea is, could we use this kind of intuition to make an automatic like speech extractor based on this dialogue history? And the rough idea was to feed that into a large language model and to use that context embedding to do speech extraction. So the way that we handled this in practice was via a very naive approach to see if this was even like viable. And it's pretty simple. We call this our cascaded model. We take in the mixture and we separate out the streams in it using a pre-trained speech separation model, in this case SEPformer. And then we transcribe each of the streams using, again, a pre-trained model, in this case Whisper, into transcription 1 and 2. We prepend to those transcriptions the textual context that we got from the chat, and we see which of these texts has the highest log probability according to language model, in this case Llama 3. You can see that the second stream has the highest log probability, so it's selected as our target stream. So we just extracted that stream. This is really simple, but it works pretty well. So let's look at an example here. There's some context about successful public spaces, and then there's this mixture of what comes next in the speech. In this case, we have a monologue We have a transcription of the monologue, and we want to see what comes next in this monologue.
I thought if I could
at the
answer
heart
those
of
questions,
innovation is a
I could
paradox.
make a huge contribution to my city.
So yeah, it's kind of hard to make out what was being said there, but yeah, we can separate those out automatically and transcribe those streams. And now we have these two transcriptions. And yeah, you can probably expect that the transcription that has to do with huge contributions to the city is more likely to come after this than the transcription that's talking about the heart of innovation. Then we feed these transcriptions plus the context into the LLM, and we get some scores of them for them. And indeed, the LLM score for stream 2 is higher. So we select it, and we get this.
I thought if I could answer those questions, I could make a huge contribution to my city.
So obviously, it doesn't always work this well, but we're pretty happy with the fact that even with this very weak cue, we can do proper speech extraction. But we're pretty unhappy with some of the inefficiencies in the previous model, so we wanted to propose some new ones. Looking back at what we were talking about, it's pretty obvious that we need some kind of speech separation or extraction network to do this task, and also that we need a language model to get some good language understanding of what's going on. But probably the speech recognition is not really necessary. You shouldn't really need to go from audio into text. If you could feed the language understanding directly into the speech separation or extraction model, that would be the most elegant. So that was the idea with our unified models. The first one that we presented was Contextual, or contextual separator. Basically what we do is we take the masking network from Sepformer. This receives the mixture of audios, which is omitted here. And we feed it the context embedding. The context embedding is extracted by feeding the context into an LLM and taking the last hidden state. This is concatenated in the attention mechanisms naively in both of these layers. And then we have the usual mask predictor, where we predict the mask 1 and mask 2 for the separated streams. But also we have this new target predictor, which predicts basically 0 or 1 to predict whether the target stream should be stream 1 or stream 2. This is particularly useful in situations where we want to keep both streams, but we want to choose which one is the target. So for example, if we want to extract the target stream, raise its volume, and then put them back together. If we're not interested in that, then we can do it in an even simpler way. We can just feed the context embedding into the Sepform architecture, but instead of having those two prediction heads, we can have a single one that just predicts the target mask for the target stream. This we call context or contextual extractor. We also present a hybrid version of context. In this case, it takes in not only the context embedding, but also optionally the speaker embedding. Speaker embedding is what I was talking about before. It's extracted from an audio sample from the target speaker, and it's a much stronger cue. But this is useful because there will probably be scenarios where we have only context. There'll be scenarios where we have only an audio cue, and there'll be scenarios where we have both, and we should leverage both. So this flexibility can be useful. In practice, we train and evaluate on 2 dialogue datasets. One of them is Daily Talk, which is really clean, but really short and only has 2 speakers. So it's good for a proof of concept. Then we have Spoken Was, which is more realistic, but quite noisy. But it has a lot more speakers and hours. And we also experiment with one monologue dataset, which is TED Liam 3, recorded from TED Talks, has a lot of speakers and hours. During training, we mix 2 or 3 utterances randomly to kind of simulate the speech interference that we're looking for. And we vary the SNR randomly between -5 and 5. All of the models that we presented so far are trained on all of these datasets separately. To evaluate, we use 2 pretty common speech extraction quality metrics, which are scale invariant signal to noise ratio improvement. This is improvement over the noisy baseline, also known as SISNRI, and also signal to distortion ratio improvement, or SDRI. We also want to measure speech extraction accuracy to understand if we extracted the correct target stream or not. And we measure this in percentage, where 100% would be the upper bound, where we always predict the right stream, and 50% would be the lower bound, where it would be random. The way that we compute the ground truth for this accuracy is a little bit tricky, but there are more details about that in the paper. Now, onto the results. First of all, we present the oracle and the random speech separators that we talked about in the previous slide as a kind of upper bound and lower bound for our model. You can see that the oracle does really well because the accuracy is 100% because we did it manually. And the random one is really bad. The accuracy is really low. And also the quality metrics are really degraded by the wrong predictions. We also present a target speech extraction model as an upper bound. This has the audio cue, which is much stronger than the context cue. So obviously the results are going to be really good. Moving on to the CSE models, which are the new ones that we present, you can see that context, so the most kind of simple of our models, actually does the best on most of these benchmarks, which is really good. You can see the cascaded model doesn't do great on spoken was, which has a wider variety of accents. And so a lot of the errors from speech recognition are propagated into wrong predictions. But on something like Ted Liam, which has a more narrow amount of accents, the cascaded model actually does pretty well and actually outperforms concept and context for a couple of these metrics. Moving on to the hybrid model, it also does pretty well. When we have context only, it performs pretty similarly to what we have above, of course. When it has only audio, it performs pretty similar to the target speech extraction model. And when we have both, it actually outperforms the audio-only cue. Obviously, this is a really tiny improvement, but it's pretty remarkable that a very strong cue like an audio recording from the speaker can actually be augmented by this much weaker cue of using the text. And obviously the fact that it can use either cue or both is a really big advantage in practice. Let's look at some audio samples now. We have this context about a conversation. Then we have this input.
It doesn't matter. You gotta find what she's interested in and go with that.
And here are the contextual separation results.
It doesn't matter. You gotta find what she's interested in and go with that. It doesn't matter. You gotta find what she's interested in and go with that. It doesn't matter. You gotta find what she's interested in and go with that.
And here's the target speech extraction result, which is kind of the upper bound.
It doesn't matter. You gotta find what she's interested in and go with that.
So they do pretty all right, but you might have noticed that there's a little bit of bleeding on some of these of the non-target stream, and we're aware of this limitation, and this is something that we want to work on in the future. In terms of the context length, we do some ablations on how long the context is and how this affects performance. So we vary the number of turns in the dialogue history. You can see that as we increase it from 1 to 10, the performance goes up really a lot higher. And this is because with more turns of dialogue, the LLM has more sentences to understand what the conversation is about, and therefore it can perform extraction well. But of course, at around 50 sentences, this becomes a bit, or 50 turns rather, this becomes a bit saturated, and the LLM has understood what the conversation is about. We also experiment a bit with other LLMs, smaller ones, and we found that actually the smaller OPT models that we tried, that are a bit smaller than Llama 3, 8 billion, actually impact performance by quite a lot, and performance is substantially worse, which kind of suggests that CSE is actually quite bottlenecked by the performance of the LLM, and it's very important to have an LLM with strong capacity to perform this task well and understand the context. So yeah, that's pretty much our method. We've presented this new task of contextual speech extraction in this paper, and we've shown that it's viable as a speech extraction method without the use of any other explicit cues. Obviously, in scenarios such as mobile messaging, this is a lot easier for the user than having to record a separate audio recording, and we don't need to be storing anything apart from the text messages that are already there. But as I said, the model still struggles a little bit with bleeding from the non-target stream, so results aren't perfect, especially compared to normal target speech extraction. Some potential improvements are a better backbone. We use SEP-Former as a proof of concept, but it's not the state of the art anymore. Also, we'd like to experiment with noisier conditions with more interfering speakers. And also, we'd like to try some better injection methods of the context into the network. What we do now is naive concatenation, but if we use cross-attention, that might be a lot better, or some other more intricate methods as well. We would also like to experiment with more data sets, or even with synthetic data where we could use text-to-speech on an existing dialogue data set to generate a spoken dialogue data set that we could use for this task. And yeah, that's pretty much it. Thanks a lot for watching. Here are the links to our project page, to our paper, and to our code. Thank you.